Thank you, Drink Club. Thank you all for coming back so punctually from lunch. I haven't given this kind of lecture before, so it may be very bumpy, I hope not. But I am delighted to have the opportunity to think back to 30 years ago when I was with Pople, and to recount and recollect what was going on in his group at the time. But I need to put this in the context, so let me first of all tell you a little about John Pople. He was an Englishman. He was born in 1925 and died in 2004 in Chicago. He surely ranks among the greatest quantum chemists that we have seen yet, and this was recognized by his half of the Nobel Prize in 1998. And the way that I will present his connection with DFT today is in 4 parts, where he began a skeptic, became an enthusiast, returned to being a skeptic, and finally became a knight, which is what happens at the end of the day. And I was reflecting on this and that pattern, and it reminded me, perhaps because I'm a strange person, of Antonio Vivaldi, who was born in 1678 in Venice, which is sort of Italy, not at that time. Died in Vienna, 1741, ranks among the greatest Baroque composers, and is best known for his 4 seasons concerti: spring, summer, autumn, winter. And I'm going to try to present John's involvement with DFT in a seasonal framework for your approval, I hope. So the outline of the talk, first of all, we will discuss spring. What was the situation before John was lured into playing the game? Summer, which was the period of maximum activity in Pittsburgh. Lots was happening. It was a very exciting time in the Pople zone. Autumn, which is when things started to cool a little, including John's enthusiasm and perhaps by infection, my own. And I will not say too much about winter because winter is a sad season, so we will not dwell on that. That's going to be the structure of my talk. But before I begin, it's interesting to see how tangled the timelines were of Walter Cohn and John Pople and their common denominator in Carnegie Mellon University. So in 1923, Walter Cohn was born. That was 182 years after Vivaldi died in Vienna. Walter Cohn was born there. 1925, John Pople was born in England 282 years after Newton died there. 1938, Walter Cohn was moved to England during the so-called Kindertransport. David Clary has apparently written a book about Walter Cohn's life, so you can read more about this, no doubt, in that. In 1950, Walter moved to Carnegie Mellon University, and in 1960, he left Carnegie Mellon to go to the western coast, University of California, San Diego. 4 years later, the famous paper appeared, the Hohenberg-Cohn paper. And that same year, John Pople left England, bound for Carnegie Mellon University. The following year, the Cohn-Sham paper appeared, which is the basis of what most of us do now. And in 1988, I went from, where was I before that? In Australia, to become John's final postdoc at Carnegie Mellon University. And in 1998, John Pople and Martin Head-Gordon and I traveled to Stockholm, not far from here, for the Nobel Prize ceremony. Dennis Salahope was there too. And in 2004, after John died, his Nobel medal was bequeathed to Carnegie Mellon University. So it's interesting to see how the timelines of these 2 men and the university were interwoven. So it is spring. This is the period before 1990, which from Pople's perspective, was before there was DFT. That's probably deeply insulting to some people in the audience, but I am simply presenting another man's perspective. So what was the situation as he saw it then? Well, in 1965, there had been this famous paper by Cohn and Sham, which had said that everything can be done in a what looks like a Hartree-Fock sort of mathematical formalism, but not only do we have exchange, but we also have correlation. Great news, but only an existence theorem. So existence is easy, one might say. The proof is certainly not a very complicated one. The problem was, from Pople's point of view, one can't do anything with just an existence proof. One needs something much more constructive in order to be able to generate numbers. 1981, I was still an undergraduate, John Perdue published this paper, which I found very agreeable. The reason I liked this paper was that the part that I've highlighted in yellow at the bottom, this was an expert in the field saying, we are facing a hard problem. Existence was easy, but construction of this functional is hard, no question. And the particular point that John Perdue was making in this paper was that the helium-like ions, as the nuclear charge is increased, have a correlation energy that tends to a constant. The beryllium-like ions, as the nuclear charge is increased, have a correlation energy which increases linearly without bound to plus infinity. And John wrote here, correctly, it's very hard to imagine how you could make hard to see how any a priori electron gas approximation could reproduce both of these behaviors in these fundamentally simple systems, a 2-electron system and a 4-electron system. However, 7 years later, a green shoot emerged. A paper was published by Axel Becker, north of the border, Canada, on a functional for exchange parameterized to fit the inert gases, atoms, and with only one adjustable parameter, which was surprisingly accurate for such a simple uniparametric functional. At this point, some people, including Pople, took note of what was happening, but no action, just took note. That same year, south of the border, in Chapel Hill, this paper was introduced. Whitehour showed us this paper, this paper a couple of hours ago also. An important paper, a correlation functional this time. Both this one and the previous were gradient corrected functionals, one for exchange and one for correlation. Also in 1988, a Polish gentleman, Jerzy Cieslowski, published this Physrevlet, where he proposed a general way forward using Mel Levy's prescription for such things for generating density functional energies in a variational sort of way. Looks fine until you read the abstract, and then you start thinking, okay, I need a complete set of arbitrary functions in order to make this work. That's probably not going to be trivial to come up with. Nonetheless, again, people took note, I took note, and wondered who this strange person was who had written this PRL. 1989, I had moved to Pittsburgh to join John's group, and one of the first things that I did was to jump in a car with Martin Head Gordon, and we drove a long way from Pittsburgh to St. Augustine for the Sanibel meeting. And when we were there, we met and had coffee with a young Pole called Jerzy Cieslowski. I thought to myself, what a great opportunity. I can pick his brains about the merits of DFT and that Physrevlet that he had just written and find out what was going to happen next. So I asked, tell me about the merits of DFT. I don't know much about this. What do you think? And Jerzy's comment was, the future for DFT is bleak. it can't even get helium-like and beryllium-like ions right. He basically cited John Perdue's paper. Well, I was working on wave function things with John Pople, so I was happy to hear this. I think that's called confirmation bias these days. I made a mental note to myself, okay, density functional theory is a dead end. Yeah, she says so. Axel Becker also gave a talk at this Sanibel meeting about what he called basis set-free density functional theory. The path to basis set-free DFT is to use an enormous basis of Dirac delta functions, and the calculations were slow. And I made another mental note of that. So I left the Sanibel symposium distinctly unimpressed with what I had heard, and thinking, well, I'll stick to my 2 electron integrals. Back in Pittsburgh, Pople unveiled the first of a series of well-defined models for calculating molecular energies. The first one was called G1. G stood for Gaussian, probably an unfortunate choice. And this was a general purpose method which could be applied in principle to any molecule, in particular to smallish organic molecules. And as you can see from the tail end of the abstract, it was accurate. And accuracy, the authors here, Martin, you were one of these authors, wrote greater than 2 kcals per mole. I think what they meant was less than 2 kcals per mole, better than 2 kcals per mole. So this was an achievement compared with very well characterized experimental data. John Pople clearly felt that he was on top of things, had a methodology which people could use and solve the world's problems. However, a couple of years later, actually, there's this Menton meeting, which we've heard about a couple of times already, where John first heard these results. They were published February of 92. Axel Becker proposed a density functional approach, which he called LSDA-GC, which is local spin density approximation with gradient corrections. Nowadays, we would call it a GGA. And he compared the results that he obtained with his method directly with John Pople's calculations using the G1 and actually by then G2 theories. This was the first time this had happened. This was a direct threat coming from density functional theory towards the wave function apex in Pittsburgh. The wording was threatening. The average absolute error for LSDA-GC, Axel wrote, is 3.7 kcals per mole, very respectably small. Our theory does not match G1 and G2, but it's not inordinately worse. Factor of 3. It's considerably simpler than the G1 and G2 procedures, which involve basis set corrections, multiplicit corrections, a quadratic configuration interaction correction, and a fitted high-level correction. In contrast, Axel wrote about his own approach, extremely simple exchange correlation functional, and no adjustments of any kind. John Perdue asked me over coffee this morning, what was it that brought John Pople into this DFT world? And basically it was a turf battle. DFT was safe from John Pople as long as it didn't invade his territory, but here Axel was walking directly into Pople's tent and saying, I'm competitive. Thanks to ChatGPT for this little image. I asked for an image of Yoda, but I was told by ChatGPT, no, that's not allowed. There are commercial and intellectual property. So it said, I can, however, do a small, wise, green being. And I said, that'll do nicely. So this is ChatGPT's version of Yoda. So, summer broke. It was time to take this threat seriously. And the first question, of course, was to establish, was Axel Becker playing fast and loose with the facts? Was he cooking the books? Were his numbers trustworthy? So we got to work coding this up in a local version of Gaussian so that we could do direct comparisons with Axel's numbers. And this paper, September 1992, just a few months after Axel's paper appeared, we reported that indeed we could reproduce Axel's number. Axel was vindicated, his reputation remained untarnished. And in the process, we had introduced a combination of functionals, Becker's 1988 exchange functional with the Li-Yang-Pa 88 correlation functional, which turned out to be a very happy pairing, and which we called BLYP, and Nick Handy called Blip, and subsequently both names have been used. This paper reported that we could reproduce the not exact numbers that Axel had, because we were using different basis sets and different functional, but that we could model the G1 and G2 molecules with the same sort of accuracy that Axel was seeing. Well, John immediately said, we are not doing yet what he would like to do. He was a very systematic person, a mathematician by training, and said, all right, both Axel's calculations and ours have been done non-self-consistently. So Axel Becker's approach was to do an LDA calculation and use that density, plug it into his exchange functional or someone else's correlation functional. Our approach was to do a Hartree-Fock calculation and plug that density into BLYP functionals. So Axel had used LDA, we'd used Hartree-Fock. John Pople knew that it was important to remove this deficiency. Looking around the room. There he is. Yes. So the asterisk is there for Kieran, because perhaps this is not a deficiency. There are some who have said that perhaps it's actually quite a good idea not to use self-consistent densities. I would say the jury is still out on this. Kieran will probably have more to say about this. We went ahead and figured out how to do self-consistent cone-sham DFT calculations within a finite basis set, and furthermore how to construct analytically the gradients with respect to motion of the nuclei, so we could find, we could optimize structures analytically with an arbitrary GGA type functional. We used this, this is a little diagram copied from this preliminary paper that I think was mentioned earlier on, where we paired three different treatments of exchange, three different treatments of correlation with two different treatments of exchange to make what would now be called rung 0, if you like, rung 1 and rung 2 functionals. The high point you see there on the rectangle is the BLYP, which is a gradient-corrected exchange with gradient-corrected correlation. This paper presented results self-consistently calculated now that confirmed again that if you did things self-consistently, the agreement with experiment became even better than it had been before. Also in 1992, it's a golden year for John, we published a paper called An Investigation of the Performance of a Hybrid of Hartree-Fock and Density Functional Theory. I look back now at this paper and its title, and I think that this was I think what Paula called in the taxi this morning a missed opportunity. We failed to do what Axel did a few months later, which was formally to combine these two together to make a rung 4 hybrid. There was Axel's initial foray into the field. He called it half and half, where he blended Hartree-Fock exchange with local density functional theories to make the first rung 4 functionals. We also needed standardized quadrature grid. Everything needed to be standardized. We were using standardized basis sets. We also needed to use standardized grids. It wasn't sufficient for John Pople to use adaptive grids which grow where they need to grow and whatnot. He wanted everything to be completely well defined from the beginning of the calculation to the end. You knew exactly what you were going to use. We introduced SG1, standard grid number 1, with a plan that there might be additional standard grids in the future, and there have been, and these are now built into various software packages. We started applying our code. This was exciting. It was fun to have discovered what the DFT fuss had been all about, running long behind many other people, but really enjoying it nonetheless. We teamed up with Gustavus Guzria, Krishnan Rakavachari. Calculations on clusters of carbon were done. This was a C20 paper. There was a subsequent C24 paper. A couple of years later, a paper was published on what I call here the importance of being unrestricted, the need that if one is doing calculations on radicals and one wants to be able to model, for example, ESR spectra, one's Kohn-Sham determinant must be spin unrestricted. A spin restricted one won't work. John Perdue published a similar paper at a similar time. And in 1996, we started work on what would now be called range-separated functionals. Back then, we were calling them Coulomb-attenuated functionals, basically functionals which are designed to do the right thing in the short range part of the Coulomb operator, not the entire operator. So these were happy times. We were in the zone. There was a lot happening. But as so often happens, seasons overlapped. And before summer had even ended, autumn was beginning. That's fall for any Americans in the audience. Even from 1993, there were concerns that perhaps not all was well in the state of Denmark. So 1993, John and I had a discussion. This was at the same time that we were working out the theory of Kohn-Sham, the general SCF theory for Kohn-Sham. We realized that there was a unique GGA that would work for the hydrogen atom, one GGA in the universe that would get the hydrogen atom right. And what I mean when I say get the hydrogen atom right is not only calculate its energy correctly, but also calculate the orbital exactly right. E to the minus r is the correct answer. And one can, it is laborious, I can tell you, one can solve this problem and find, sort of reverse engineer, what must the functional be so that when you feed it the hydrogen atom, you obtain the right answer. And this was a depressing paper. You can read the second last sentence, a very short abstract. The functional bears very little resemblance to any of the commonly used exchange functionals, even in its asymptotic behavior. We had hoped when we began this, we might see something which we could use to tweak Axel's B88 or something like that to make it work for the hydrogen atom. But the U-shaped curve there is the G of X, the, whatever you call this factor in a GGA. And you can see also Dirac's, or I shouldn't call it Dirac's, I should call it Bloch's functional, and Sham's functional, and Becky's functional. And you can see exceedingly little similarity between them. And this U-shaped curve, which works perfectly for the hydrogen atom, is a complete disaster when applied to anything else. This was sobering stuff. The DFT dream, I think we heard this morning, to try to predict everything from the density and its gradients. Probably this shows that that is a pipe dream, the nightmare of this paper. Actually, this is a special case of the self-interaction problem, because when we ask DFT to give us the right answer for a one-electron system, all it has to do is successfully kill the Hartree energy, which is completely spurious in a one-electron system. And in 1994, we published this paper where we used John Purdue's SIC, self-interaction correction, to study some hydrogen abstraction reactions because there were real problems with the barrier heights due to these self-interaction errors. We've already seen this paper, I think, also from my talk earlier today. 2008, many, many years later, people are still grappling with this problem. It is one of the great problems, probably the great problem in DFT, how to deal successfully with this self-interaction in its various manifestations. John was also concerned about rotational invariance. The orientation of a molecule in space should not affect its energy, but it does in a DFT calculation where you are using a laboratory fixed quadrature grid. As the nuclei move and the grid doesn't move, the energy changes. And so we thought about how to devise rotationally invariant procedures for doing Kohn-Sham calculations, but it was ugly and awkward and didn't feel nice at the end. We managed to solve some of the problems, but some remained stubbornly. 1996, I think this is one of John's lesser known papers, certainly one of the lesser cited papers. John was interested in taking a density for a system and breaking it into different pieces. In particular, the core density and the valence density, which one can more or less identify in a molecule. And by applying density functional theory separately to the core and valence parts to find where the energy was coming from and to compare that with wave function theories, ideas of where the energy comes from. And we found, perhaps not surprisingly, although the total is good when one uses B-lip or something else, where it's coming from is all wrong. Too much energy is coming from the core and too little from the valence, or the other way around. So the density functional partitions problem, this is not one that people have really grappled with as seriously as they probably should, but it also diminished John's enthusiasm for density functional theory because, to quote Ernie Davidson, one should be getting the right answers for the right reasons, not just the right answers. Well, somewhat depressed by this point, John said he felt that density functional theory, although it had had many successes and was likely to have many more, was likely to be a method that needed to be empirically tuned. And this brought John back to his fairly early days in the 1960s when he was doing semi-empirical molecular orbital theory. And thus began the descent into parameterization. So we published a paper which was unashamedly or ashamedly entitled Empirical Density Functionals, and we called this particular functional EDF1, which didn't bode very well because we expected there would be an EDF2, 3, 4, 5, and 6, and there have been, not with those names, but with other names. And John was resigned to finding functionals that performed well by fitting to experimental data rather than in the hard-nosed way that he would have preferred. We showed in this paper that this functional with this modest basis set outperformed, for example, B3-lip, which had already become very popular by then, but it required parameterization. As you all know, things only got worse with time, and certain people in our community have embraced this whirlpool with great enthusiasm. Others have embraced it with lukewarm enthusiasm, and others have been repulsed by it. But we have found ourselves sucked into a vortex of fitting again against experimental data to make sure our density functionals perform as well as they possibly can. And all hope, it seems, has been lost for deriving things from first principles, doing things properly, which is the way that a mathematician like John would have liked to do them. A couple of years later, on a day when I got out of bed on the wrong side, I suppose, I decided to write an obituary declaring that this subject had died from hyperparametric disorder. And a number of people have praised me for writing this. Others have abused me for writing this, what you get when you write something like this. But density functional theory has by no means died, as we all know, but it has changed its face from its earlier versions to its modern incarnations. And it is, according to John Pople, definitely a sophisticated semi-empirical theory these days. 2002, the year after the obituary, I co-organized a conference in Nottingham where I had a position at that time. It was called the Exploring Modern Computational Chemistry Conference. And we invited John to come and speak at it, and he did, which was jolly decent of him, because he was in much demand at that time. And this photo was taken, I think, when John was explaining to me some terminology that I hadn't heard before. So he said, you are familiar, of course, with semi-empirical models where the number of parameters is roughly half the number of observables. And you also are familiar with empirical models where the number of parameters is equal to the number of observables. But, Peter, he said, have you heard previously of sesqui-empirical models where the number of parameters is 1.5 times the number of observables? Winter arrived, and I don't want to spend a lot of time in winter, the last 3 years of John's life. He lost his beloved wife, Joy. She had been his piano teacher. More on that this evening. In 2003, he was knighted by Queen Elizabeth, no longer also with us. And the following year, 2004, he died peacefully in Chicago. John is gone, 20 years this year, but he leaves behind a formidable scientific legacy in 4 different areas of chemistry. He also leaves a very active academic family behind and hundreds of memories that we carry around with us. And I prefer to remember him in the good days rather than remembering him in the winter. This was a photo taken in 1999. We had something called the Pople People Party, PPP, on Amelia Island. Is that Florida? Somewhere near Florida, I think. Organised by Janet Delvane. Janet is second left there. My wife Elizabeth is on the far left. Martin Head Gordon in a blue t-shirt, as usual, in the middle. And that's John and Joy, Joy in front of me. These are the memories we have of John, a great man, a great scientist, and it's been a pleasure recollecting all of this with you. Thanks for listening.
Well, thank you, Peter, for this wonderful talk. Any thoughts here, comments or questions? Yeah, Martin?
Just a very brief comment. John once told me about slightly empirical models, which have on the order of a constant number of parameters, and he considered G1 and G2 in that category.
That is exactly right, yes. So if the number of parameters is bounded with respect to the size of the periodic table, then yes, John called it slightly empirical.
So I have a question. So what is the number of observables in density functional theory? And so how would one classify these functionals, like Martin's functionals with what, 8 or 9 parameters? So if the observable is energy, or the density.
So I guess the number of observables in density functional theory is the number of measurements that an experimentalist can make. It's a very large number. And if one can model all of that with 8 parameters, one has done very, very well.
So then these are semi-empirical functionals.
Slightly empirical, that's right, because it's still at the order of 1.
it's clear one needs to have one needs empirical parameters, but it's a very good idea to try to limit them as much as possible, whereas in reality it has increased from functional to functional, which has not led to better results or improvements. So I think one should stay with the smallest number one can.
I very strongly agree with you, and so did John Pople. I suspect that the other John would also agree with you. You're right that there's been an alarming tendency for parameters to proliferate. This is the whirlpool that ChatGPT kindly drew for me. I would certainly prefer that we not go there, but the reality is that if you have a very, very large number of parameters, you can fit almost anything, and that makes some people happy. It shouldn't make people happy, but it does.
I like to tell a story. John visited me in spring '92. He was invited to rise as a Franklin lecturer, and he motivated me to DFT. He showed me Axel's results and the preprint of the blip paper, and I ran some calculations. You helped me implement integration, and in a couple of weeks I was comparing blip in the hybrid version with CCSE parenthesis T, and the comparison was really good for activation barriers and things like that. But the story I wanted to tell is that John, I think, G2 had an empirical parameter, right? And this adjustment for the number of pairs, and and he told me that he was really impressed by the fact that Axel didn't have any empirical parameters, and that was that was like a dagger in his heart. He felt that not only DFT was giving good results, but it was coming without any empirical parameter.
Just the comment about the hydrogen atom work, I'm trying to remember it. So you said that the exchange energy needed to be minus the Coulomb energy. And the
More than
potential
that, the potential needs to be minus the potential.
Coulomb. Yes.
That's much harder.
So if you were to change your requirement there and you were to say make the energy minus the Coulomb energy divided by the number of electrons, and then you take the functional derivative of that, differentiating the n, then you do get a jump. You get a shift there of j over n squared, which will turn the potentials that you had, your negative of your Coulomb potential, and it will suddenly look much more like the Becker exchange potential.
Oh, that's
that does
nice
happen.
to hear.
That does that. And of course, I think minus j over n is a much better exchange functional than minus j. It's Fermi-Hamaldi. It's still not very good,
Yes.
but it becomes more of a global functional.
Thank you, David.
John first, and then.
So here, I wanted to ask you, in your opinion, did John Pople change his opinion of density functional theory at the one-time meeting, or was he already moving in that direction?
Prior to Monton,
To what extent?
I think in my abstract, I think I'm remembering correctly, I used the word skullduggery because John suspected that there was skullduggery in the claims he had heard earlier than Monton. But Monton was the first time that he thought, perhaps there isn't skullduggery here, maybe this is actually legit. So I suppose seeds had been planted prior to Monton, but Monton was the first time he took it seriously and returned to Pittsburgh energized in a slightly negative way.
I understand.
Pople.
I had a question on the paper you mentioned, where does the contribution of DFT to the energy comes from? So yes, I was wondering why was this disturbing? Because in a way, energy density is not uniquely defined. So what's wrong if you have a different gauge for the energy density with different contributions?
So I suppose one could think of a neon atom, for example, which has a core of a couple of electrons and 8 electrons around those. The relevance would be if you were thought about neon 8+, where you've ripped off that outer atmosphere, you would want your functional to be treating the remaining 2 electrons well. Otherwise, neon 8+ will not be well modeled. And in fact, neon 8+ isn't very well modeled because that core contribution is not right. It's underdone or overdone, I can't remember. And the valence is compensating for it, but if you remove the valence, you lose the compensation, and so it's a fragility in the method. That's how I would describe it.
Okay, so it's
Oh.
an error cancellation.
Yeah.
Okay, let's close. I just add that many of us in the Nordic countries cherish the cold winters.
Thanks so much.